In this video, we're going to derive how pressure and temperature changes as a function of altitude in the atmosphere. We're going to assume that the atmosphere is isentropic, meaning that there's no heat energy transfer and it's reversible. So we're going to start off with our first equation right here, which is the basic statics equation, and this is dp over dz equals negative rho times g. And this is saying that the gradient of pressure as a function of position is equal to the negative density of the gas times the acceleration due to gravity. So I'm just going to write that right here. And then we're going to use our ideal gas law right here, PV equals RT, to solve for density in this equation. So we're going to end up having dP over dZ equals negative PM over RT times G. P is the pressure, M is the molecular weight, R is the gas constant, T is the temperature in Kelvin, and G is the acceleration due to gravity. After that, we are going to move T to the other side and P to the other side. So then we get T over P times dP, which equals negative M over R times G times dZ. Next, we're going to integrate. So we get, we want to integrate because we want to substitute temperature in terms of pressure. So we get the integral of T over P times dP integrated from P1 to P2, and that equals to negative M over R times G times the integral of dz integrated from z1 to z2. And then we're going to integrate the second part, and I'm just going to move that over here. So we get the integral of t over p times dp from p1 to p2 equals negative mg delta z all over r. And so we're going to come back to this equation, and we're going to focus on the first law of thermodynamics, and that's right here. And this is because the gas we're dealing with is an ideal gas. The equation we're going to use focuses on internal energy. It is du equals delta Q minus P dV. And this is the internal energy per mole, and that equals a small amount of heat transfer minus the work, or plus the work. And the work is minus in this because the volume in the system is increasing, meaning that the system is doing work on the surroundings. And that is why the work is negative for us. With this equation, we're going to use the ideal gas law to solve for the pressure. So we will have du equals negative RT over P times dV. We're going to replace du with CV because that equals dQ over dt. So we get CV times dt equals negative RT over V times dV. We're going to end up integrating, so we get CV times the integral of dt, which is over t, from t1 to t2, and that's going to equal negative r times the integral of dv over v from v1 to v2. Next, we're going to take the natural logs of both sides. We'll get cv natural log of t2 over t1, which equals negative r times the natural log of v2 over v1. Here we will be solving for temperature to get to the pressure equation. We're going to have the natural log of T2 over T1 equal the natural log of V2 over V1 to the power of negative R over CV. We're going to exponentiate now, and we get T over T1 equals V over V1 to the power of R over CV. We're going to put in the ideal gas law again, and I'm going to move this up here, and get T over T1 equals RT over P all over RT1 over P. And this is raised to negative R over CV. The R's in this are going to cancel out, and then we're going to end up with T over T1 equals T over T1 times P over P1, and this is raised to negative R over CV. And then we are going to multiply both sides by T over T1 raised to R over CV. We end up getting T over T1 raised to the power of 1 plus R over CV, and that's equal to P over P1 raised to R over CV. Then we're going to combine this equation and we get T over T1 to the power of Cp over Cv, and that equals P over P1 raised to R over Cv. Cp over Cv is the ratio of specific heat capacity at constant pressure over the specific heat capacity at constant volume. This ratio is going to be denoted as gamma from now on, and so we're going to replace that Cp over Cv with gamma. So we get T over T1 gamma equals P over P1 raised to gamma minus 1 over gamma. Oh, sorry. Since this R over CV is equal to gamma minus 1, we're going to be solving for T, so we end up getting T equals T1 times P over P1 raised to gamma minus 1 over gamma. Now we have an equation for temperature, and we're going to plug this in to the equation that we derived earlier, and I'm going to start up here for that. And plugging in the temperature into this equation, we get the integral of T1 times P over P1 raised to gamma minus 1 over gamma. And this is all over P, and it's multiplied by dP. And this is integrated from P1 to P2. This equals negative mg delta z all over r. Next, we're going to move our constants outside of this integral to the left, and we're going to get T1 P1 raised gamma minus 1 over gamma times the integral of P raised gamma minus 1 over gamma times dP from P1 to P2. And I'm just going to change my marker, and then this will look a little bit better, so bear with me. And so after getting a marker that didn't die, this right here, I rewrote it. This is after I put the constants outside of the integral, and so this is going to equal negative mg delta z over r. Next, we have 1 divided by gamma minus 1 over gamma times p to the power of gamma minus 1 over gamma, solved from P1 to P2, and this equals negative mg delta z over RT1 multiplied by P1 to the power of gamma minus 1 over gamma. Solving this, we get P2 to the power of gamma minus 1 over gamma equals P1 gamma minus 1 over gamma, and this is multiplied by 1 minus gamma minus 1 over gamma, also multiplied by mg delta z over RT1. Finally, we take the root of both sides and get P2 equals P1 multiplied by 1 minus gamma minus 1 over gamma multiplied by mg delta z over RT1, and this is to the power of gamma minus 1 over gamma. This is the answer to the relationship between pressure and temperature as a function of altitude in an isentropic atmosphere. Thank you.